Hello students, so today we'll be going into the next topic. So let us brush up what we have discussed in yesterday's class. In the last section, so we have looked into the maximum a posterior hypothesis. We have seen the Bayesian theorem, right? And how from maximum a posterior hypothesis now we are deriving to maximum likelihood hypothesis, that is, which is called as the H of M L. So the posterior probability, that is probability of D for a given set of data given a particular hypothesis, now is often called as the likelihood of the data D given in hypothesis S, and we say that this is the maximum likelihood hypothesis, which is nothing but the argmax of probability of all D given H. So now this is our posterior probability, now which can be found by using Bayesian theorem. Now let us take an example and try to understand how all these concepts have been applied. So now what does the example says, right? Now consider a medical diagnosis problem in which there are two alternative hypotheses. Right, now we are defining two hypotheses, two alternative hypotheses. Now what does the first hypothesis says? Let us call it as H1. Now what does the H1 say? That this is defined as the patient has a particular form of cancer. Patient is suffering from cancer in a very simple term. The alternative hypothesis H2, what we are defining H2 as, H2 is nothing but this is H1 I can call, and this is, let us assume, let's call H2. What is the second hypothesis we are defining? That the patient does not suffer from cancer, right? So patient, the first hypothesis says the patient is suffering from cancer. The second hypothesis is telling that patient does not has the cancer. Now we have some available data with us. Now what are the data available for us? Now the available data is from a particular lab test. Now there is a lab now where they are going to conduct some test on the patients, and that particular lab test gives two outcomes. So only two possible results the lab is going to give. One is positive, the other one is negative, right? I think you are very clear that when positive means the patient is suffering from cancer. If the result comes negative, he is not suffering from cancer. This is the available data. Now, as we know that to apply Bayesian theorem, so we need some prior knowledge, right? Now, we have a prior knowledge that over the entire population of people, only 0.008 have the disease, right? So, when you consider the entire population, now this is the prior hypothesis, prior knowledge what we are having. So, it is telling that 0.008 have this disease. That means 8 out of 1000. 8 out of 1000 people is suffering from cancer. So 8 by 1000 is 0.008. So 8 people out of 1000 are having this particular disease. And furthermore, now it is given that the lab test is only an improper indication of the diseases, right? So it is the improper indication of the disease. That means, so the lab test, whatever they are giving the lab test, now it is not a proper, improper. That means sometimes wrong also they can diagnose. So we can't rely on this lab test, right? So now it is given that the lab test is only improper indicator of our disease. So we cannot completely rely on this. There are chances that the results may be wrong. So now in that scenario, when a new instance comes, now how do you classify? How do you say that out of these two hypotheses, whether he has a cancer, whether he has not a cancer, right? So what are the things you know? That the lab is going to give you the result, and we also know that the lab result is not a correct measure, it is not an proper way or indicator, it is improper. There is chances that the results, whatever the result the lab people are going to give, it might contain error also. And also we have a prior knowledge that 8 out of 1000 people generally suffers from this type of cancer. Now we have some other data is available for us. Now what are that? Let us look here. Now the test, when they conduct the test on the patient, the test returns a correct positive results. It returns, listen carefully, it returns correct positive results in only 98% of the cases in which the disease is actually present. Right? So 98% of the cases in which the disease is actually present. So that means correct positive results. The lab is going to give the result, and when you are going to get the result, now we have one data. What that data says that if the patient is having cancer, lab is going to give a positive result. How? 98%. 98% that will be correct. If the patient is having cancer and the lab result is telling that he is cancer, 98%. That means still 2% error is there. 2% of the chances are there that the patient may be having cancer, but the lab result will tell negative. The 2% chances, right? Because 98% correct positive result it is telling. So if correct positive result is 98%, then 2% it might be correct negative result. Correct negative result is having cancer, but test is telling negative, right? The next data what we are having, the test returns a correct negative result only in 97% of the cases. In 97% of the cases, correct negative result. That means the patient is not suffering from cancer, and the test also is telling that negative report. The lab test is giving negative report. That means it is correct, genuine, right? He is not having cancer, and lab report is telling that he is negative. That means in 97%. That means still 3% is there. 3% chances are there that the patient really does not has any cancer, but the lab report is telling positive. Right? So you have seen. So we have seen that in the COVID cases also, when we conduct RT-PCR test, in one lab they tell positive, in one lab they tell negative. So that percentage we are taking here. So 97% correct negative result the lab is going to give. So in other cases, the test returns the opposite result. That's what we told. In this case, 2% will be the opposite result. In this case, 3% will be the opposite results. Right? Now, these are the data what we are having. Now, with these data, now we will calculate some probabilities. Right? So, we are going to calculate the probabilities. Look into the notations carefully here. The first one, P of cancer, probability of cancer. Now, we had a prior knowledge which says that out of 1,000 people, 8% is having the cancer. You look here, this data is given in our problem. So, where it is given? It is given here. Right? Over the entire population of people, only 0.008% have the disease. So, probability of cancer is how much? Now, 0.008. If probability of cancer, that means out of 1,000 people, 8% is suffering from cancer, means how many people are left over without cancer? 992. Right? So, the probability of negation of cancer, that means probability of patients not having, in our population not having cancer is how much? So, it is 1 minus of 0.008. This is how we calculate. So, 1 minus of 0.008 is 0.992. Right? So, now this what we calculated. Next, probability of this symbol. This indicates that positive results, right? Plus and a small circle. So, the probability of positive, right, given that he is having cancer. So, positive results about, that is the correct positive result that the patient is suffering from cancer. How much? Already it is there in our problem. Where it is there in our problem? Look here. The correct positive result in only is 98%. 98% means what? 0.98. So, probability of positive result given, that means he is suffering from a cancer is 98%. Then how many percentage is not suffering? So, that means that is the opposite of that. That means the probability of minus circle given that he is having a cancer is 0.02. 1 minus 0.98, 0.02. Already we have discussed. Right? So, 98% of the time the lab is giving correct result. That means patient is having a cancer and it is diagnosing him as positive. There are chances that 2% the patient is having cancer, but they are giving negative report for us. So here we are going to write it as minus and circle. Even though patient is having cancer, but it is telling negative. How many percentage? 2%. Now similarly, probability of positive when is not having a cancer. Right? Now this is given. See here, 0.97 is what? Probability of negative, correct negative is not suffering from cancer is 97%. So 97%, the lab is telling that the patient is not having cancer, even though in reality he does not have cancer. But 3% chances is there when he is not having cancer, negative of cancer, but the lab is telling positive. So lab is going to indicate that now he is having a positive, but actually he is not having cancer. How much percentage? 0.03. Right? So this is 97%. The 1 minus of 0.97, you get 0.03. Now these are the sum of the probabilities. Now what we have calculated. Now suppose we observe a new patient from whom the lab test returns a positive result. Right? Now a new patient comes to the lab. Now they does the test and the lab is going to give a positive result. Now when a positive result is given, now should we diagnose this patient as having cancer or not? Whether this result, positive result, will obey our hypothesis 1, which says that he is suffering from cancer, or the second hypothesis which says that he is not suffering from cancer. You cannot, since the lab is giving us the positive result, now you cannot take it, because you know that the lab test is not the final test. There will be some errors in the lab, right? How much percentage and all we have calculated now. Now, how you are going to diagnose that whether he is having a cancer or not. So now we are going to apply our most MAP, most a priori hypothesis, or maximum a priori hypothesis. Now what is that equation? Says HMAP is equal to argmax for all the hypotheses belonging to H of probability of D given H into probability of H. This is the equation. So now we will use this equation for what? For all H belonging to H, for all hypotheses belonging to our hypothesis set. Now how many hypothesis set are there? How many hypotheses are there in our example? 2 hypotheses, H1 and H2, as we are told. H1 is patient is suffering from cancer, H2 is patient not suffering from cancer. There are 2 hypotheses. So for all H belonging to H. Now we will take the first hypothesis. Now this is for first hypothesis, and we are going to calculate what is this RHS. Now we will calculate this. That is probability of D given this hypothesis into probability of the hypothesis. So for when you consider the first hypothesis H1, so what will be the probability of D data, right? The probability of positive result given that he is having a cancer, because hypothesis 1 is what we have, it is stating that the patient is suffering from cancer. So we will take the data related to cancer only. So probability of positive given he is having a cancer into probability of cancer. Right? Cancer is our hypothesis. Now you can see here probability of H. Here also H is there, here also H is there. This is our data D. So what is this data D? So it is positive or negative. 2 types of result the lab test is going to give. A positive result or a negative result it is going to give. So probability of positive result given whether he is having a cancer or not a cancer. But right now first hypothesis is with cancer. Now is equal to, so now already we calculated this. So probability of positive, correct positive given cancer is what? 0.98 multiplied with the probability of a cancer. How many people are having cancer? That is prior knowledge, 8 out of 1000 people, that is 0.008. Multiply these two, you get the value 0.0078. Right? We calculated H map for H1 hypothesis. So now that is we calculated this for H1 hypothesis. Now you calculate for similarly for H2 hypothesis, second hypothesis. What is H2 hypothesis? hypothesis, patient is not suffering from cancer. So now probability of plus, right, positive result, what it is going to give patient for a correct when he is not suffering from cancer, multiplied with probability of the patient not having cancer. So which is equal to, so now probability of this plus given that he is not having the cancer is how much? 0.03 multiplied with probability of not having cancer 0.992. So you are going to get 0.0298. So now you calculated this right hand side posterior probability. So we call this as posterior probability, right? So we calculated this posterior probability. How you got this equation? From Bayes theorem. So already in the previous section we have seen the derivations and all, right? So now you calculated for both. Now you have to apply this particular max R for both of these. So you just apply which one is maximum out of this. So because you want to calculate H map. So H map is equal to how much? What you are going to infer. So whether you are going to conclude that patient is having cancer or whether patient is not having cancer. So now when you look here, now which is maximum out of this two values, two numbers we are having in front of you, right? 0.0078 and 0.0298. Which is maximum? H2 is maximum. So H2 is maximum. So R max of all H belonging to H. Out of these two, which is maximum? This is maximum. So what is this related to? This is related to second hypothesis. What is this hypothesis? This hypothesis says that patient is not suffering from cancer. So what you are going to diagnose that from this particular problem. So what is the question which is asked? The question will be whether the patient has a cancer or not a cancer. Now what is your result? So your result will be that patient is not having a cancer because this hypothesis H2 is maximum. Based on this, so we are going to conclude that he is not having cancer. The patient is not having or not suffering from cancer. This is how a simple example. So now like these type of examples you can expect in the in your examination. So clearly understand the concept, so then it is very easy for us to calculate and try to solve this particular example. So this was the concept what we have discussed about the Bayesian theorem, Bayesian learning, why it is important in machine learning, what are the features of Bayesian learning. Then we discussed or we gave a statement for Bayes theorem, right, and maximum a posterior hypothesis HMAP. So then with the maximum a posterior hypothesis we came to maximum likelihood of hypothesis when all the when we don't have any prior knowledge. So now this is what till now we have discussed. Now we are going for another concept, Bayes theorem and concept learning. Now we already discussed what is concept learning in our first chapter or module 1. So we have discussed concept learning. Now we are trying to put this Bayesian concept with the concept learning. So what is concept learning? Concept learning in a very simple term already we have understood that. So you are making a machine to learn. You give some concept, right? So you are going to give some concept, you give some training set of data. With this training set of data, now your machine will start learning, concept learning based on some concept. Then when a new instance comes, the machine will be able to classify this instance correctly. It can either accept or it can reject. It can classify correctly. That is what we call it as the concept learning. Now how we are going to use the Bayes theorem and the concept learning, how we are going to link or how you bring our Bayes into the concept learning. So what is the relationship between Bayes theorem and the problem of concept learning? So this is what we are going to understand and try to come up with an equation where we are going to combine both of things. Now posterior probabilities can be used. So we know that posterior probability. What is posterior probability? That is what Bayes theorem is giving, right? Probability of the given data set, the given a particular hypothesis holds good. We calculate this by using that equation. So Posterior probability can be used as a basis for a straightforward learning algorithm that calculates the probability of each possible hypothesis. Then out comes the most probable one. What our posterior probability is telling us, now we can apply this posterior probability to any straightforward learning algorithm, now which calculates the probabilities on each hypothesis. So in the example we have seen, we took hypothesis H1, we calculated the probability, posterior probability. We took hypothesis H2, patient is not having cancer, calculate the posterior hypothesis. Then like this H1, H2, you will be having so many hypotheses will be there. You have to calculate the posterior hypothesis for all the hypotheses, and out of all those things, which is maximum, we call maximum posterior hypothesis. Now this maximum posterior hypothesis, now we are going to consider. That is what till now we have discussed in the previous section, right? So we can apply this concept, we can apply this posterior probabilities. Now it can be used as a basis for our straightforward learning algorithm. Now we will see how we can use this in our concept learning. See what concept learning is telling. Concept learning tells us that you give one concept, right? You give some training example and you train. The machine starts learning based on this training example. It learns something to classify any new instant, whether it belongs to which particular classification, right? So which, based on the features, it starts learning. That's what the concept learning is talking about. So now we will try to understand some of the basic formulas now which is required for the calculation, or try to understand with respect to our Bayesian theorem or the probability. So some of these formulas we will be using later. So first one is what? So product rule. Now how do you define? All these are the equations comes in our basic probability in your mathematics, right? So first, product rule. What is this product rule? Probability of A and B. So you have two events A and B, probability of A and B. So this is also called as conjunction of two events A and B. How do you define probability of A and B? Is equal to probability of A given event B, right? So this is probability. How do you read this? Probability of A given event B multiplied with probability of B, which is equal to probability of B given A. B given A multiplied with probability of A, because and is there, conjunction, you have to add both this event. So what we call it as a product rule in our probability. Probability of A and B is equal to probability of A given B into probability of B, which is equal to probability of B given A multiplied with probability of A. Now similarly sum rule is there. Sum rule means sum is what? Probability of A or B, or disjunction of two events A and B. So how do you give the sum rule? Probability of A or B is equal to probability of A plus probability of B minus probability of A and B, conjunction of these two, right? This is the sum rule, and this is the Bayes theorem. Already we have discussed this. Probability, that is the posterior probability of H given D is equal to probability of D given H into probability of H divided by probability of D, where D is the data set. And another very important theorem is the theorem of total probability. If event A1 to AN are mutually exclusive events, so if you are going to consider mutually exclusive events, now what do you mean by mutually exclusive events? So these are the events which cannot occur simultaneously. Say for example, if you toss a coin. Now when you toss a coin, what is the outcome you are going to get? You will get either head or tail. These are the two events, right? Event A1, event A2. A1 is head, A2 is tail, let us assume. Now mutually exclusive events means, now this example, what output you are going to get, A1 and A2, can we get both simultaneously? If you toss a coin, do you get both head and tail? It is not possible. Either you should get head or you should get tail. Both are not possible at any instant of time. That is why we call mutually exclusive. if you consider such a type of an example where all the events are mutually exclusive, then we can apply the theorem of total probability. Now when you have got the equal chances, when any one mutual exclusive is there, then we will try to sum. So we will try to find the summation for I is equal to 1 to n. Probability of AI is equal to 1. So we are going to sum. That is what we told already in our previous class, that if you don't have any prior knowledge for all the hypotheses, now we are going to assign equal probability, equal chances, right? So we are going to give the equal chances to that. So when you have the equal chances, when you sum up all these things, so you are supposed to get 1. That is the fundamental theorem of probability. Probability of an, if you have got an event A and an event B, then probability of A plus probability of B should be equal to always 1. So when you find out that, because those A and B are mutually exclusive event, so then we can say theorem of total probability as probability of B is equal to summation for I is equal to 1 to n, how many experiment you are conducting, probability of B given AI, right, for all these events 1, 2, 3, 4, given AI multiplied with probability of AI. So this is the formula of theorem of total probability. So when you can apply this, only when the events are mutually exclusive events, right? So with these fundamentals, so now we will try to understand now how the concept learning can be combined with your Bayesian theorem, right? So or how we can apply the Bayesian learning to our concept learning. So we are going to start with the first one, which is called as brute force Bayes concept learning. So you know what is the concept of brute force in our algorithms, data structures you already studied. This is one type of a problem solving technique. Brute force means trial and error. So we don't have anything. So we take this as a fundamental, and from here we start improvising our algorithm. So now what we are going to say is that we are going to start without any prior knowledge. We just try to apply our concept learning and Bayes. So we try to combine the concept learning and Bayes. So which we call it as the first basic method, that is brute force technique. So very simple one, very straightforward. Now we can design a straightforward concept learning algorithm to output. Now what we want maximum a posterior hypothesis, right? So we want a maximum a posterior hypothesis based on our Bayesian theorem. Now what does this brute force concept learning algorithm says? Now you can see it is a very simple algorithm which consists of 2 steps. What is the first step? For each hypothesis H in set of all hypotheses, calculate the posterior probability. How do you calculate posterior probability for all the hypotheses in our hypothesis set? By applying Bayes theorem, right? So what is that? Probability of the H given D is equal to probability of D given H. So right, for the one hypothesis, so we have seen an example for a hypothesis whether patient is suffering from cancer, we calculate. Then second hypothesis, not suffering from cancer. So probability of D given H multiplied with P of H divided by probability of D, set of all data samples or training examples. So you calculate the posterior probability. So the second, output H map. So you are going to calculate this posterior probability for all hypotheses which are belonging to your set of all hypotheses capital H. You will be having many hypotheses in our set of all hypotheses. For all each hypothesis, like say H1, H2, H3, etc. up to Hn, you calculate the posterior probability. Then output H map, right? Maximum a posterior hypothesis. So what is the equation to find H map? You have to find the maximum. Whatever here in the previous step, so like say for example, you have 3 hypotheses in our capital H, H1, H2, H3. Now what you do? You take first hypothesis H1, calculate posterior probability. Then you take second hypothesis H2, calculate posterior probability. Take third one, calculate posterior probability. Now you have posterior probability of all the 3 hypotheses. Now you calculate H map. What is H map? Argmax. maximum out of these three. Posterior probability, what result you got in previous step, arg max of all h belonging to H of probability of H given D. So what is this probability of H given D? This is nothing but your posterior probability which you have calculated in your previous step, right? So that is what the algorithm says. Now let us see, try to understand. Now let us choose P of H and P of D given H to be consistent with the following assumption. So now we have to make some assumption here. So we are going to have based on, so we say that posterior probability and probability of the given hypothesis P of H and P of D given H. Now these two are consistent with all the hypotheses. To have that consistent, to tell that consistent, we should have some assumptions here. So we know that concept learning, so when you are going for a concept learning, we try to have some assumptions and we start learning. So now what are the assumptions we are going to make? The first assumption, the training data set D is noise free, right? So that is D of I is equal to C of Xi. So that means we are going to assume that whatever data set is given to us, it does not contains any error, does not contains any missing value, right? That's what we call noise free. The second assumption is the target concept. So you will be having some target concept, right? So this target concept C is contained in the hypothesis space H. When you are considering the hypothesis space, our target should be one among the hypothesis space. So target concept is contained in the set of all hypotheses. And the third assumption is when no prior knowledge is given, when you don't have any prior knowledge, right? When we have no prior reasons to believe that any hypothesis is more probable than any other. So we have no prior reasons. So without any prior reasons to believe that any hypothesis is more probable than any other. So right now we cannot sell that one particular hypothesis is more probable than any other, right? So that is what are the, we are treating all the hypotheses at the same at the initial point. So now given these assumptions, what value should we specify for probability of H? Right? What is that probability of H? See, probability of D given H, you know, we have equation we can calculate. Now probability of H is prior knowledge. With some assumptions, now we try to put that prior knowledge. So we want to calculate the prior probability with some assumptions. So we are making these assumptions and we try to see how we can calculate probability of H. That is very important because to apply the Bayes theorem we need prior probability, right? Now given this assumption, what value should we specify for P of H, right? That is what our question is. That now when no prior knowledge is there, that one hypothesis is most likely than another. See, when you have got two hypotheses without any prior knowledge, now how you can tell that H1 is better than H2? Right? You should have some prior knowledge to us. So without any prior knowledge that say 90% of the people suffering from pandemic diseases, they will recover, without that knowledge, how you can tell that yes, who are all got this COVID, everybody is going to recover? We cannot come. So given no prior knowledge that any one hypothesis is most likely than the another, now it is reasonable to assign the same probability to each hypothesis, right? We are just trying to understand this from our previous section also. When you don't know whether H1 is having more likely to occur or H2 is most likely to occur, what we can do? When you are going to toss a coin or when you are going to roll a dice, you don't know what the output you are going to get, what is the likelihood of occurrence. At that time what we do, assign equal probability for all the hypotheses. So now what we are saying, so we are going to assign equal, same prior probability. So assign same, where is this cursor? Assign same prior probability to every hypothesis H. Further, Because we assume that the target concept is contained in H. Already we have assumed that target concept should be in set of all hypotheses. Since we have assumed that, now we should require that these prior probabilities sum to 1. Now when you are assigning all the probability in equal chances, so then obviously when you are going to sum, now it is going to become 1. How? Based on one of the probability theorem, like most when the events are mutually exclusive events. Already we have seen that. So when you are going to find the sum, it should sum up to 1. Now with these constraints, now we can say that, how we can say what is your probability of all the hypotheses, probability of H. Now we can say which is equal to 1 divided by modulus of capital H. That means now for all the set of all the hypotheses, right? So now say that now when you roll a dice, simple example, try to understand. When you roll a dice, what are the outcomes you are going to have? So you will be getting one number out of 6 numbers. So totally six-sided face is there in dice. You are going to get 1 out of 6. So now what is the chances that when I roll a dice, I am going to get number 1? What is the probability? What is the chances? I don't have any prior knowledge. Without any prior knowledge, because I am not a Shakuni, right? So I don't have any prior knowledge. When I roll a dice, you don't know what will be the outcome, whether 1 comes or 2 comes or 3 comes, you don't know. So what you are going to assign? So what is the total number of outcomes? 6. So what is the probability that one I might get when I roll a dice? So I will say 1 by 6. 1 by 6. What is the likelihood that 2 is going to come when I roll a dice? Again it is 1 by 6 only, right? Why 1 by 6 only? Because there are only 6 outcomes. I am assigning equal probabilities. So for getting number 1, chances is 1 by 6. For getting, when I roll a dice, getting number 2, chances is 1 by 6 only. For when I getting number 3 is once again 1 by 6. Like that 4, 5 and 6 is 1 by 6. When you add up all these things, you are going to get 1. So that 6. Similarly, what is that 6? The total outcome. When I roll a dice, either I should get 1, 2, 3, 4, 5 or 6. I cannot get 10 because there is no 10 marked on our dice. So here you just look now, the probability of H is equal to 1 divided by modulus of H. So in our set of all hypotheses, like how for a rolling a dice you have got 6 outcomes. So when you consider the set of all hypotheses, how many hypotheses you might be having? You might be having 6 hypotheses or 1 hypothesis, 1, 2, 3, 4, 5, etc. Some set of hypotheses are there. So you find the modular. That means you are going to find totally how many hypotheses are there in your set of all hypotheses. So 1 divided by total number of hypotheses. Right? Now this becomes our probability of H. So what is the probability of H1? Suppose this is one hypothesis contained in capital H. What is the probability of getting this H1? Now this is equal to 1 divided by, go back to your rolling a dice. What is the probability of getting number 1 when you roll a dice? Equal to 1 divided by how many? 6. Why 6? Because there is only 6 outcomes. Now here 1 divided by how much? How many hypotheses are there in my set of all hypotheses, right? How many hypotheses are there? So you take capital H, the total number of all hypotheses in our capital H. So that becomes H1. What is for H2? Again it is same. What is for H3? It is same. So probability of H equal to 1 divided by set of all hypotheses in our hypothesis space. So for all H belonging to capital H. Right? So it is very simple, try to understand. So now the probability of the data, now you take the data sets. So now the probability of this given data set for a particular hypothesis, the probability of data D given hypothesis H, we say is equal to 1 if D is consistent with H, right? So whenever you take some set of hypothesis some set of training data set, and based on this particular training data set, if suppose say that you are telling the hypothesis, say for example you have got one hypothesis which says that 80% of the students pass the first internals. On what basis you can tell 80% of the student pass the first internals? If that is my hypothesis, I need some training data. I take last semester or two back what all the internals you have written, right? So I take all those data set, previous past history, I take and I calculate, and I come to know that yes, in all the tests, so they 80% are passing, right? So now when you take another set of data, now what we are telling is that we say that the probability of this data which is consistent with that hypothesis, which is telling me that 80% of the students is going to pass the first internals, if it is consistent, we assign 1 to that. If it is consistent, if my data set is providing me 80 or more than 80% students who are passing the first internal, then my hypothesis is correct. It is consistent with that hypothesis which says that 80% is passing first internal. So then we are going to say that it is consistent. So when it is consistent for this given data set, if my hypothesis is consistent, I am going to represent it as 1, otherwise 0. Straightforward, right? Either accept or reject, right? Now here you see what we are writing. Probability of this data D given this set of hypothesis is equal to 1 if Di for individual data of your capital D. So if Di is equal to H of Xi. That means you take first student's marks. How much marks he got? He got above 80% in first internals, equal to H of Xi. Hypothesis what? Above 80%. You take first student, what is the result? Above 80%. Okay, next student, what is the result? If it is below 80%, put him down. You just keep on classifying. Once you have classified into two groups, then you find the how much is there, that probability. If it is greater than 80% of our entire class, so then you mark it as 1, otherwise you mark it as 0. So we say that if Di is equal to H of Xi for all Di in H and 0 otherwise, right? So this is very now clear for us. Now let us consider the first step of this algorithm, now which uses Bayes theorem to compute the posterior probability P of H. Now given this data set, now I have the hypothesis, right? Now what is our hypothesis? Just now I told 80% and above passing the first internals. For that I am having some training data set. For this training data set, whether this hypothesis holds good, right? Of each hypothesis S given the observed training data D. So now we are going to apply the Bayes theorem. So now probability of H given D is equal to, how we apply, now if you apply Bayes theorem for this LHS, now this will be probability of D. Here you can see here it is reversed. So probability of D given H multiplied with probability of H divided by probability of D, right? This is very from our Bayes theorem. Now the posterior probability of a hypothesis inconsistent with D is 0. Already we told, if it is consistent we are going to mark 1, if it is inconsistent we are going to mark it as 0, right? So we take this, the posterior probability of a hypothesis inconsistent with D is 0. So now consider the case where H is consistent. If it is inconsistent we are going to mark 0. So you leave it. Now we are talking about consistent. Now consider the case where this hypothesis is consistent with D. So if it is consistent with D, so then how do we rewrite this above equation? So probability of H given D is equal to, now you look into the numerator, right? So now what we are having, now probability of D given H into probability of H. Now this is, the numerator is replaced with, now what is probability of D given H? What is the probability of D given H? So what is that? We are saying that for a given the probability of your entire data set, when it is consistent with your given hypothesis, then we are going to represent it with 1. It is consistent, right? For a probability of D given the hypothesis, when it is consistent, we represent it as H. And what about P of H? What is this P of H? It is nothing but 1 divided by total number of hypotheses in our set of all hypothesis space. So in the previous also already we wrote this, right? So this numerator is replaced with 1 into 1 divided by set of all hypotheses divided by denominator P of D. Now this further it can be simplified as is equal to 1 into 1 by H divided by, now what is probability of D? Now you look into your denominator. Now what is our denominator? It is telling probability of all our training data set irrespective of hypothesis. See, P of D only, we are not attaching any hypothesis with respect to some hypothesis. You are not seeing, you are just seeing probability of your data set. So when you are going to look into the probability of only all the data set irrespective of hypothesis, now that probability of D, it can be replaced with set of all hypotheses in our version space, VS, set of all hypotheses for the given data set, training data set D. From where we got this? Remember, go back to your first module, concept learning. In concept learning, we defined what is called as a version space. So now we are going to consider version. What is that version space? All hypotheses which are consistent only we are considering in our version space. In our, when you discussed candidate elimination algorithm, try to go back to your first module, try to read that, right? So the probability of D, now this denominator, now it is replaced with all the consistent hypotheses with respect to the given training data set in our version space we are going to take, divided by set of all hypotheses. That means totally how many hypotheses are there. So this is our denominator, that is probability of the data set D. So now we substitute this here. So now further when you simplify here, this and this can be cancelled and we are going to get 1 divided by set of all consistent hypotheses in our version space with respect to the given data set is equal to 1 divided by version space H comma D if H is consistent with D, right? Whenever H is consistent. If it is inconsistent, see here 0. Clear? So now to summarize our Bayes theorem, which implies that the posterior probability of H given D under our assumed probability of H and probability of D given H is given as. So now we are going to replace this. Now we are going to summarize this, which is called as a brute force MAP learning algorithm. So in the examination, if they ask you explain brute force MAP learning algorithm, so you have to explain all these things, and this is our final equation. So how you are going to say probability of H given D, which is equal to, we told, see here we told it is 1, right? So here we told it is 1. Now this, what is this 1? When it is consistent, now we are bringing that. What is that 1? It is nothing but 1 divided by set of all consistent hypotheses, that is total number. So when you say, see this is your version space H comma D, all the hypotheses which are consistent with respect to this training set. Now when I use this symbol, so I am going to count the number. So totally how many are there if H is consistent with that, and 0 otherwise, right? So this is what brute force MAP learning algorithm. So try to once again try to read this and as well as look into this video session carefully. So once you have understood, in the next section we will be discussing evolution of probability associated with our hypothesis. So how we will try to look into this, some of the interesting things. Now how you are going to see the evolution of these probabilities. So when you are going to have some hypothesis, and when you look into the training example, why we say training example is very important for us, that we will be discussing in our next topic. So before we discuss the next topic, so I request all of you to just once again try to understand, read and see the concept learning and Bayes theorem. Now how we have integrated, or we can say how we try to bring the concept learning into our the Bayes theorem into our concept learning. Okay, so just try to read and look into the videos, and whatever doubts is there, you can just drop the doubts in our Google Classroom. Thank you. Have a nice day. Bye bye.